To Lagoon K, we have abusing bleeding edge web standards for Appsec Glory. In here we've got Brian Zadigan and Ryan Lester. Before we begin, we've got a few brief notes. Stop by the business hall located in Bayside A and B during the day for the welcome reception, and that's from 1730 to 1900 tonight. The Black Hat Arsenal is on the Palm Foyer, Level 3. Join us for the Pony Awards in Mandalay Bay, BCD at 1830. And thank you for putting your phone on vibrate. Your cell phone ringtone is not as cool as mine. Thanks, guys. Go ahead and start.
Cool. All right. Well, now that you're all settled in, I hope you've all had a chance to visit our website.
Hold on, wait, so why did you go with this for our hands-on demo?
Well, I mean, it was actually literally the absolute last domain available. I didn't have anything else, so...
Nice. So let's assume that the demo gods hate us today. What actually happens if they visit ISIS.io?
All right.
Or what should happen, because it could very well be failing right now.
Fair enough. So when you go to ISIS.io, you will...
It's off.
It's off?
Wonderful. Something always goes wrong. All right.
So this is what you should see, just basic static site. And if you go here now, this actually is the beginning of the hands-on component of our session, which we will revisit later on.
If you're getting worried about getting on a watch list, don't worry. I think Ryan is probably a little bit high up on the list because he was the one that actually decided to buy the domain. So, all right. All that being said, so welcome to the room. I hope everybody enjoyed the keynote that we missed. As Andy said, this is Abusing Bleeding Edge Web Standards for Appsec Glory. My name is Bryant.
I'm Ryan.
This is Ryan, exactly. Just a quick primer on who we are. Twitter handle in case that's something that's relevant to people. My background, I do application security stuff usually. I mentor security startups for a firm called Mach 37 sometimes. I mentor others on application security. There are air quotes for those in the back. Less frequently. And once upon a time, I paid $1 to somebody to make the person make Steve Ballmer dance on stage, but that was just once.
And I'm Ryan. I'm the CEO and co-founder of an end-to-end encrypted communication startup called Scythe, which was actually the origin of a lot of the research that went into this talk. I'm also more or less the chief architect and primary developer of Scythe. Before Scythe, I was a software engineer at a rocket factory called SpaceX. And at one point, I was sued by Napster for alleged trademark infringement.
Should I get that story from you right now?
No, it's all right.
Are you, prohibited from giving the story?
There are some details that I am prohibited from.
Fair enough. All right. So, bleeding edge web standards. So, here's what we're going to do. We're going to focus on 3 web standards that most of you have probably heard about, and a good number of you have probably had some experience with if you're in this room. But let's talk about the word abusing first. So we're talking not just about abusing, hacking in a classical sense, like most people, like breakers, are likely familiar with. We're also talking about hacking together, like what developers, builders would be familiar with. So putting together a project very quickly or finding a really novel use case for technologies that are readily available to you, right? So we're going to focus on sub-resource integrity, but specifically we're going to focus on something called SRI fallback. That's our name for it. Content security policy, we'll touch on that. And if anybody's not familiar with content security policy, it's just client-side last layer of defense for code injection in your browser. So you can set rules on what things can and cannot execute based on what you've deployed to your, for your application. And specifically, we're going to talk about something that we're calling CSP meta hardening. It sounds cool. We'll go into detail as we're speaking. Lastly, HTTP public key pinning, which some people may be familiar with. We'll go into more detail as we speak. And the specific abuse case here, and this is actually half the talk, is going to be something that we're calling HPKP suicide. So why are we talking about this? That's not what I want to do. All right, so here's the thing. New standards have been coming out left and right. So the W3C, IETF, what have you, are drafting new standards on a very frequent basis, on a very high cadence. The Chromium team, the Mozilla, to some extent Microsoft, have been implementing these standards as quickly as they could. And here's the thing. When you're introducing new standards at this pace and implementing them at this pace, unforeseen use cases can develop, and it's also a very ripe opportunity for people to target them for bug bounties. So, you know, things can go screwy when you're going this fast. So when you start building web applications or modifying your apps for these standards in interesting new ways, it actually helps to drive the development of these and future standards going forward. So I guess we can dive into SRI right now.
Mm-hmm. Right, so one of those standards that Brian was just talking about is called SRI, Sub-Resource Integrity, and it's just a way for you to is it not working?
There it goes.
Okay. It's just a way for you to validate the integrity of resources hosted outside of your zone of trust, like a CDN. So in this example, we've got a script source there that's loading jQuery from the jQuery CDN, and a set of possible hashes that it could hash to for integrity validation. And if it were provided by the spec, we would also have a fallback source for when that hash check fails.
Am I being obnoxious by using the laser pointer? Whatever, doesn't matter. All right, so...
Right, so the closest the spec actually gets toward providing fallback SRC is giving general guidance on how it might be implemented, but they don't actually provide a direct solution to doing that. So we went ahead and built it for you.
Yeah, so... Actually, yeah, go ahead.
Right.
It's all yours.
So our script is called SRI fallback, and it just gives you this little XSRI fallback attribute, which you can add to any script or style sheet in your HTML.
So the goal here then is if you were to use this, you would probably point this at a resource, like a backup resource at a location that you trust.
Exactly.
And it would still validate against the existing hashes that are on the actual...
Right, so you would want that to be hosted on the same local origin as your code,
right,
as opposed to a CDN.
So I guess we can go through a demo failed proof, time permitting, right? Because we want to get to the good demos at the end. But we will link to the source if anybody is up for pictures. But we'll also have a link at the end of the talk that's going to have every link that we've got in this talk. So, all right. But I think, did we end up going through this? Yeah, we did. Okay.
Yeah.
So here's a good example of just a very quick finding that we came across while we were in the midst of creating this talk, while we were putting this together. We came across a in our mind, trivial vulnerability that netted us a very easy $2,000. Google ranked it a high, and it got us some nice and easy cash, which kind of speaks to our point. It's really easy when you start looking at new standards being put out to grab a few quick bucks. So take it from here.
Sure. So this was actually, it was a caching bug in same origin SRI in an older version of Chrome. We've got a demo here in BrowserStack using that old version of Chrome. You can see there is two buttons, one that injects a script tag with a valid hash and one that does an invalid hash.
We'll zoom in when we get to the actual cool stuff.
Right. The invalid hash, you can see there, gives you an error as expected, integrity fail. And then, one more. Is it not working? There we go.
There we go.
Clicking it again then works. And, well, yeah, so first time fails, second time works. You might have cases where you're doing like infinite scrolling on a website where it loads the same script multiple times, and that could trigger this. So
yeah, so Google called it a high, fixed it really quickly, threw out $2,000, problem solved. All right, that was easy. I mean, that's the thing, is if you guys are breakers, you guys are considering bug bounties, target the new security standards that are being built. So, I mean, it's quick and easy cash. So, moving on. That was quick. So, CSP meta hardening. What we mean by this, if you're familiar, show of hands. Who's familiar with content security policy? That is a very great population in the room. Okay. So, if you know CSP, you know that when the headers, like the way you set the policies are through HTTP headers, right? Something that most people don't know is that you can also set the policy through meta tags. This is essentially what this is we're combining semi-strict, or what we would call semi-relaxed actually, headers, CSP headers, with the strict headers in meta tags that you actually want. And this allows for preloading of trusted complex logic. And we'll give some examples in a bit. The meta tags, like the meta use case for CSP, doesn't allow for certain verbs like frame ancestors, report URI, or sandbox. So if you happen to be using that, that's kind of out of the question. But I think we've got a very quick pre-scripted demo, a demo God proof demo again.
Right. So like the other one, it's right there if you want to see it live. But got some screenshots here. So it shows the current CSP, which allows for self, current origin, or unsafe inline scripts. 3 buttons: test inline code, test non-inline, or remote code, and then there's a third button that'll do some CSP meta hardening. So the first button works as you expect. Second button also works as you expect. And then we, with that third button that we clicked, injected a meta element that removed unsafe inline from the CSP.
Literally injected the meta element right into the DOM.
Right.
And the second that happens, the browser recognizes it and evaluates the rule.
Mm-hmm. And after that, you can see clicking test inline code, now that unsafe inline is no longer in the CSP, gives you a CSP error.
So here's the cool thing. You can only harden your actual policies. You can't relax them. So you can't, for instance, have a super strict policy that might neglect something and then somebody finds XSS through whatever you neglected and then relaxes all the rules to open up a wider exploit. You can't do that. You can only harden your content security policy if you've implemented it. And the use case here is this. Let's say you're a typical Silicon Valley shop. You're focused on, developer shop. You're focused on creating an MVP, a minimum viable product. Security might not have been the first thing to really come to your mind. What you can actually do is you're looking back retroactively at hardening your tool, hardening your product, and you can do all of the preloading of the static trusted content that you have, all the resources that you actually trust that aren't user modifiable, right? You load all of that, let's say in like a single page application type setup. And once all that's loaded, then you harden your CSP with the meta elements. And at that point, then once it's hardened, you can start trusting the potentially user-controlled content, the data that users might have saved, names, email, whatever, stuff like that. And your risk of XSS is dramatically minimized. So this is a good way to harden much more complex applications. I know that there are a few companies that have used this approach. I'm not certain enough to name any of them on stage, so I won't do that. All right. So this is, I think, the bulk of the talk that we've got going. So we're going to focus on a lot of things with HPKP. And I guess because I'm expecting familiarity with HPKP is probably less. So let me get a quick hands up as to how many people know what HPKP is. Yeah, so it's going to be a little less than CSP. HPKP, HTTP public key pinning, it can brick sites if you misuse it. It used to be that it could dramatically brick your sites a lot worse. But Google and I believe Mozilla as of right now, if there's anybody from Mozilla in the room that can confirm if this went to prod, you can tell me, have reduced the max age, the absolute maximum max age that you could set to 60 days. It used to be that you could set that to a year, which means if you screwed up HPKP and people pinned the wrong cert, they'd be locked out for like a year. So let me condense this for the room then, since we have a large population that isn't actually familiar with this. HPKP lets you pin a hash of the key that you're serving out for your TLS connections. That way, once a person visits your site for the first time, it's like trust on first use. They then say, okay, I'm familiar with this key. This is the only key I should be trusting from this server for this period of time. That's what the max age is for. The tack on includes subdomains. Every subdomain that's underneath the domain that you have the headers on will also be checked against that full list of hashes. You should have at least 2, one being a backup, one for the main domain, and you can have, I think, as many as you want.
I think so.
If you're going to implement this, do it with reporting first. Do it with reporting first, because that way you'll know if you messed up. If you don't do it with reporting and you mess up, you're going to kick yourself. So there, that's the quick primer on HPKP. So let's dive into HPKP suicide. What? So here's the thing. This is a deliberate self-bricking. You're literally intentionally bricking your clients by coupling HPKP with rapid key rotation or rapid rekeying. So we'll spend a quick 20 minutes on how we can use this, but you had a hat tip first.
Right. So before we continue, I wanted to give a big shout out to Jan Horn at Cure 53. He was the one who turned us on to this idea of HPKP suicide during an OTF-funded audit of Scythe last summer. And also DigiCert, before Let's Encrypt was a thing, they helped us implement this. Yeah.
It was actually really generous of both of them. But
yeah.
A quick 20 minutes on what we can actually do with HPKP suicide. So I struck this out for a reason. We'll explain why in a moment. To enable in-browser code signing, which is actually really cool. To control content changes and harden SRI. To enable nuanced web content blocking. If you're familiar with Blue Coat, that's the context we're speaking in. You can use HPKP suicide to track users. And you can also use it to just be total jerks if that's your thing. And this is all in ways that we really shouldn't put in print. So, a quick primer on what HPKP suicide actually looks like. Go ahead.
Sure. So here we've got just an HPKP suicide-based local content pinning scheme. So this allows you to persistently pin a web page in the user's browser. So first, the user just requests the page like any other website. In this case, we're also including an app cache or a service worker to set up a long-lived client-side cache of the page. And afterwards, on the back end, so the TLS handshake completes and so on. And then on the back end, the server is deleting its own private key, generating an entirely new one, and requesting a new certificate from its CA for that new key, and serving HPKP headers. So the next time the user hits the website, the TLS handshake will fail because it'll say, oh, this is the wrong key. And what happens then is the browser falls back to the pinned service worker and just loads that kind of like a native app. I mean, doesn't go out to the server at all. The browser thinks the server is offline, essentially.
Yeah. So this actually happens, this happens below the actual presentation layer in the browser. So when you send a request to a site and that site has a service worker already cached in the browser, then that service worker then handles the request. But of course, if the request fails, there's got to be error logic for the service worker to be able to say, this didn't work. That's where you can insert custom logic that can handle, that can actually anticipate that you've bricked your client's connections to your website. So we'll give the use cases. It's actually really cool. All right. What was the first one? In-browser code signing?
Yeah.
So why did we strike it out?
Right. So it should work in theory, right? You just use the mechanism we just described, only you put code signing logic in that front-end page. So you're probably familiar with the whole notion of JS crypto considered harmful and the web's trust on every use security harmful. The web's trust on every use security model, which in-browser code signing would address. So in this case, so the mechanism we just described gets you trust on first use. So go on. So why in theory this sounds like it should work? So in fact, Scythe employs a mature audited implementation of exactly this. But it was considered so novel that we were advised to apply for a patent on it at the time that we implemented it. But you can come pretty close to the benefits of in-browser code signing by following the pattern Brian is about to describe.
Yeah. So I also mentioned the second bullet was combining HPKP with SRI. And I think we probably actually will have time to potentially demo this live. But we'll see if that's embarrassing enough that it will fail on stage. So here's the thing. If you combine so SRI, of course, being used to check the integrity of resources that are beyond your, sub-resources, things that are beyond your control, that are subordinate to the web page that you just loaded. And the basic premise here is you load the service worker. Once the service worker is loaded on your first visit, that service worker has all of the references to all the other scripts and style sheets and what have you. It has the hashes and everything that you need pointing to those for those resources to actually validate correctly. And then you brick the connection through HPKP suicide, through rapid rekeying. So once the content is loaded and pinned in the user's browser, and then you rekey, the content is then pinned in the user's browser. And even if your content server, the main web server that the users are visiting, gets compromised, it doesn't matter because your users aren't reconnecting to that every single time. Once their connection has been bricked, they already have a copy of what they should trust stored locally, which also has the hashes for all these sub-resources that are also necessary for loading the page. In order to make this work, you need to rotate your keys very frequently compared to your development, like your release cadence. So let's say you release a new application once a week, you probably want to rotate your keys like once a day. The theme here being that the max age counts down to when you're releasing like a new build of your code. And that's when people's connection, their pinned keys will expire. They'll then download, quote unquote, the new version. Actually, it is still downloading. They'll download the new version of the code. You're reducing how often they have to actually trust the server for new code that's loaded. So that's a good way of guaranteeing the content that actually ends up on their browsers. This will probably get you, if I had to guess, like 85% of the way to like true trust on first use. It's not really, you don't have code signing going on, but I mean, it's pretty close. You're restricting how often they're pulling down code. So,
and to clarify the max age counting down, it's a dynamically calculated HPKP header. So at the time you hit the server to get the code, it's calculating, n seconds to Sunday 4 p.m. That's the number of seconds in the header.
Right. And again, we'll try and demo this if we can, time permitting. So, right. So the quick benefits. Okay, you're retaining control of front-end content between releases. That way, like I said, in the event that your own content hosts are compromised, it shouldn't matter to your end users. Likewise, you're also mitigating the risk of an attacker also tampering hashes for sub-resources that your code might also reference. Also, because you're reducing the number of times your clients are actually hitting your server, like the root page, you're also going to get some decent performance gains too. So here's some things to consider. HPKP suicide plus SRI, this specific pattern that we're talking about, it's a design time decision, and in my brain, I think it's for single page apps only. If you preload all the content and you don't have like pages below root. It's single page apps only, if you're familiar with the term. And on top of that, you should probably include mitigations, such as halting distribution of HPKP headers in the event that the content on your server is compromised. Because if you don't include those if you don't include, let's say, a quick hash check server side that says, this is the content that we deployed, then in the event of a compromise, you're looking at people having compromised content pinned into their browsers. So I guess, time permitting, we're from DC. That's the reference.
It's not totally random.
Yeah, it's not entirely random. All right. Web content gateways. We'll say Blue Coat. That's the one that comes to my brain. Let's say that's what you do. What you can theoretically do here is lock your users out of sites even when they're not on your network. So if they hit a site for the first time and then the web content gateway says, oh yeah, you can't visit this. Well, you've likely got SSL man in the middle going on. So for that flagged content, for those flagged domains, you set the HPKP headers. And optionally, if you want to reduce the load on your web content gateway, you can also rotate the keys weekly to have that whole HPKP suicide thing going while you're still on the corporate network. But the point is, the second any corporate user leaves the network, the pinned keys are for the web content gateway. They're not for the cert from the site itself. So by doing so, you can then block access when a person actually leaves the corporate network. Now, of course, a tech-savvy user will know how to blow the HPKP headers, but most probably won't, and most probably won't know how to go through the effort of figuring that out. So hopefully that's all we need to do to disclose this and make this prior art with no idea. That way, hopefully, everybody can go on this without actually being able to patent it. Oh, wait a second. Hold on. Okay, so VeriSign clearly. Oh, right. Yeah, so this is a bit of news where Blue Coat apparently became an intermediate CA. Well, that's okay. So I think once upon a time we've had web content gateways sold to nation states. So now you have the potential of potentially, and I'd love for somebody from Blue Coat to actually correct us on stage. We don't care. To implement this entire strategy against their own, like the actual users within the country's boundaries. Even if they leave the country, they might be prohibited from accessing certain sites. if web content gateways were to implement this strategy. So
imagine a great firewall that works outside of China. I mean, like, you go to China, then you leave, and it's still working in your browser.
User tracking. All right. So we really shouldn't talk about this. Actually, we have a good demo for this one. This is pretty cool. But since this is Black Hat, let's track users. All right. So some prereqs. We need lots of domains to pin. We're talking 32, at least. You also need browsers that allow for HPKP, like the actual pinning of HPKP headers, in incognito mode, which I believe is every browser that currently supports HPKP. We've reported this to both of them, and the more value was put on security over privacy. Personally, we disagree with this. We think if you're using incognito mode, you're valuing privacy over the added benefit of pinning certificates, or pinning keys rather. And lastly, rapid key rotation. You're really relying on this in order to make what is essentially HPKP super cookies to make this work. The easiest way we got this done was through Let's Encrypt, and we love everything that Let's Encrypt is doing. We're not trying to be like snarky when we're saying thanks. This is one place where rapid key rotation, they have like a 20 rekey limit, which is really useful. This is one place where rapid rekeying is potentially like really effective for use cases like this. So.
All right, so the general setup we're using for our super cookies, most ideas for the implementation are based on report URI. In this case, we're basing it on HPKP suicide, which, unlike report URI, is cross-browser. It works in Chrome and Firefox. So on the server, we've just got a method that spits back an HPKP header, and another method that's more or less a no-op. It does nothing. And then on the client side, setting a new ID is just hitting that set method in a random pattern. So you iterate through the subdomains and just pick ones at random to hit. And then checking the ID is also iterating through the check method on every single one of those subdomains, and then noting which ones fail, reconstructing a 32-bit integer from that. So we've got a demo server hosted at saif.wang. So our demo here, not live, this is not implemented by Google, as we noted there. It's just something we pasted the JS into the console there. So you've got this line here, supercookie saif.wang, and then it'll log the output to the console. And can you see? Okay, it zooms in. So in this case, is new user true means this was a newly generated ID. We haven't seen this user before, and the ID is 4565566, totally random 32-bit integer. And now we're in incognito on a different website, which also didn't implement this. We just pasted it into their console. And so we loaded the JS and ran the same line here, getting the cookie from saif.wang. And in this case, when I tried to check the ID, the TLS handshake failed on a bunch of those subdomains because of the invalid pin header, the suicided headers. So here, based on those failures, we reconstructed the same integer, 4565566, and we know is new user is false.
I don't know if the guys in the back can actually see it, but yeah, we've actually so here's the thing. When we're saying iterate through the subdomains, literally are iterating through them. So if you actually
0 through 31, that's saif.wang.
Right. So if you actually look, the domains that failed are that's how we're setting the actual bits that determine the user's actual ID. So what are some, quick considerations for setting this up? Well, this is a quick proof of concept. By the way, the code for this is also included. We'll have all the links as well. So here's the thing. You can have, if you set this up this kind of super cookie, you can actually have, for instance, a public benefactor of sorts come in and try and DOS your tracking domains as a public service. So you can have two easy mitigations for this. Let's say that you're only setting up this HPKP super cookie for use on your own sites. Hypothetically, let's say you're Facebook and you've got a number of different properties and you want to track whether or not somebody is visiting Facebook or Instagram or whatever, regardless of whether or not they're in incognito mode. Well, you can whitelist the origins and that should probably cover it. Now, what if you're offering this as a service? Okay, you're an ad network or you're offering analytics. Well, in that case, you can have like a tracker issue, well, it's from the tracker, but the app issues a nonce to the client, which then gets validated by the tracking domains before handing out the HPKP headers. Without that nonce, it doesn't hand out the headers, therefore you mitigate the risk of somebody going and DOSing access to 0 through 31.scythe.wang. I think that was what it was. So those are probably the two things I'd watch out for. I'm sure there's more. Again, this is very, very high level research. I'm sure there's plenty of ways this could screw up, and there's plenty more things that people can actually do beyond just this. It's also worth noting that in the actual RFC for HPKP, this pattern is kind of sort of described, not exactly, but kind of sort of described. Our implementation is, I believe, a bit different.
I mentioned they use report URI in their ideas.
Yes, they actually use report URI in the course of implementing their cookies. Whereas they also have other ways of potentially doing this. But again, in the standard, they just touch on it at a high level. So feel free to read through the standard and see what else is worth implementing. Because again, these are all things they talk about as they're putting out the web standards themselves for review. So source. If anybody cares about pictures, we can give a quick 30 seconds, I guess. But we'll also have a URL at the end that, again, has all the source links that we need. So let's see. What's our next topic? I saw some cameras open, so. All right. So what if we want to use HPKP suicide to be total jerks? Well, we really shouldn't talk about this, but, who are we kidding? This is Black Hat. So here's what you need before we get into what this actually is. You need a high traffic target, a target, that presumably has some amount of value. You probably need a way to get access to the box, and probably need a free certificate authority because, if you're paying for it, you're probably going to be traced. We're not trying to throw Let's Encrypt under the bus. Again, we love them, but they're the ones innovating here, and you can use Let's Encrypt to your ends, so to speak. So, okay, first things first. We're calling this ransom PKP because that's probably the worst thing we could think of that you can do with it. You can use this to just deny access to anybody that's actually visiting a website. If you compromise the site, you can use this to just deny people's access to it. But, or let's say you compromise somebody and you just want to deface their site. Okay, well, why deface them when you can monetize it? So there you go. So you determine your target, and you generate what we're calling the ransom key pair. This is the recovery key that you have locally. This never leaves your command and control. Oh God, did I really write poem there? Okay, you take control of your target web servers, and on the target web servers, that's when you generate the lockout key pair. This is the key pair that you're rotating on a routine cadence. You send the CSR to Let's Encrypt. There's a question mark, block, and profit. So, the sensor kind of came up late. Sorry. So what's in the box? Ryan, what's in the box?
Right. So it's really what's in the box that enables this attack. So when you rapidly rekey, you're actually committing your gains each time. So let's say, 100,000 users have hit CNN.com within the last, 10 minutes.
We're not throwing CNN under the bus intentionally, are we?
So, no, sorry, random example.
We love CNN. We're not throwing it under the, we're not, don't do that, don't do this to CNN.
Okay, I'll say food.com. 100,000 users have hit that site, while your malicious HPKP header was being served. You rekey, and then suddenly those 100,000 users are, blocked from accessing the site, and the site admins can't do anything about it.
Let me actually put some emphasis on this. When you rekey, you're committing your gains. That's the thing. You're committing your gains. What I mean by that means that whatever number of people were locked out, they cannot gain access to the site, even if the administrators of the site gain access to the compromised web server and recover whatever the most recent lockout key is that's actually used for serving the site, for the TLS connections. Because all the old keys are blown. Every time you rotate the keys, the old keys are blown. You've committed your gains. Those guys are locked out for 60 days. That's the emphasis here. That's really what makes this work.
Exactly.
So, yeah. You hit your cadence to your 100,000 users in this case. At that point, you generate your new lockout key pair locally. I mean, heck, if you can automate certbot, I think, and do this. And you get your new CSR sent to Let's Encrypt. They give you your cert. And that's it. Just reset the counter. Keep going.
All right. So do you remember when you first hit our website at the beginning of the session?
You may have not hit the website. I anticipate most people have probably not opened their web browsers or even turned on their phones. Which is probably smart.
Right. So this is what you might have seen if any of you actually visited it.
Did you actually rekey yet?
Oh, that's a good point.
That's actually probably not a bad idea.
All right. So hold on. I'm just going to...
What you will see after he rekeys the site, you can also use this as a great opportunity to own his phone if you really want to. What you will see is the wonderful page that actually tells you that you're locked out. It tells you that the actual key is not in it's not in your cert chain, the actual key that's served out. So that's your indication that you have been locked out of access to that site. You can of course fix this on your end. We'll get into that in a bit. Working? Not working?
Well, if my tubes were working, it would rekey.
Of course.
Pretend it rekeyed.
We'll handle it later. Whatever. This is what would happen in the event that he rekeyed the site successfully and you were to visit it again. You would be locked out of actually visiting the site. This isn't really an exploit against users. It's, again, an exploit against the site that's serving the content out. So some considerations, meaning why this is not a high, right? So Let's Encrypt's rate limit is, they've got two rate limits. They've got five certs a week. And if you tweak around with how you make the cert request, you can get it up to 20 times a week. There's actually a really good reason for this that we found out in conversations last night and going back. Chrome and Firefox also have HPKP lockout mitigations. They're a little buried, but you can find them, and we'll talk about them here. And of course, you still need to pop the box. So, programmatic mitigations. Of course, we sent this to the Chromium team, the Firefox team, and Let's Encrypt. Chromium indicated that it was already pre-mitigated. Like they reduced their max age to 60 days. So you cannot set a max age above 60 days, which means that if a lockout attack happens, if this ransom PKP attack actually happens, you're not going to get locked out for more than 60 days as an end user. Some companies may say, that's fine, we'll just let them, whatever. But if you happen to be, hypothetically speaking, a media, a media conglomerate and you want to cover the elections and this happens to you in October, okay. Firefox, they took the step of matching Chrome's HPKP max age, and they indicated that they're going to kind of wait and see. Hopefully this doesn't gain traction. People don't actually do this. And Let's Encrypt indicated that it's actually out of scope for them to address this because there are standards that end users, administrators, what have you, can implement to mitigate the risks here. We understand the rationale. In our opinion, it would be better if we could reduce the rekeying frequency, or at least tie the rekeying frequency to some sort of prompt. Like, let's say you hit that initial rate limit of 5, maybe send some sort of confirmation email or something that says, hey, you've already hit your rate limit. If you want to get 15 more, just do this, click this link, whatever, something. In our opinion, that would help, but we're not the experts, so we're deferring to Let's Encrypt on this one.
And I think their more fundamental argument that it was more of an ecosystem problem with various standards and this property emerging from those standards rather than a Let's Encrypt problem.
Yeah.
Other CAs could be used to do the same thing.
Exactly. Like you can use a paid CA or other CAs that will probably emerge after Let's Encrypt to handle this. So we actually had a good conversation with a rep from the EFF about this. And so again, one of the big concerns is making sure that TLS can actually be successfully rolled out. And one of the big obstacles that was observed is that when people are rolling out TLS in cases where they haven't in the past, then they tend to run into issues hitting that initial 5 cert rate limit when they're first setting it up. So having the ability to bump up that rate limit to 20 just by adding another domain to the initial set that you request has helped a lot of sysadmins to get themselves off the ground when implementing this, when implementing Let's Encrypt. That's why they're keeping it the way it is. Now, if they reduce it later, that'd be cool, but we get it. So, mitigations for hosts. Well, how many people have heard of this RFC? The DNS Certification Authority Authorization. Show of hands. Yeah, that's what I thought. It's like literally two hands went up. When we initially presented this to the 3 vendors that we noted, they informed us that CAA was something similar to one of the mitigations that we had proposed. The basic premise here is that if you use CAA, you can blacklist Let's Encrypt from issuing certs for your domain unless you specifically indicate in your DNS header, in your DNS records that you want Let's Encrypt to issue certs for your domain. So if you know you're always going to use a paid certificate authority, then yeah, you essentially say, I'm only using VeriSign or DigiCert or whoever for my certs. I'm never going to use Let's Encrypt. And all of a sudden, you've reduced the possibility that somebody can use a certificate authority other than what you've used for this kind of attack. Also, if you're already using HPKP, you're already protected. Why? Because if somebody manages to pop the box and install their own, and automate this attack, they would need to replace the keys you've already pinned in your end users' browsers, which breaks their access to your content using your known good keys. Therefore, recovery is as simple as getting rid of the infection, getting rid of the actual payload, and putting your known good keys back in.
So the worst they could do is DOS you, but they don't need ransom PKP for that.
And it's easy to recover from that too. And of course, the last and easily the most difficult is just don't get popped. End user mitigations, very, very quickly. In Chrome, you can just Chrome //net internals /HSTS, and I guess.
So there's that. That's how you're supposed to be able to clear pins. At one point, not long ago, there was a bug where clearing any part of your browsing history or cache, saved passwords, things of that nature, would clear all of your pinned keys. And this was a misplaced curly brace in the Chromium source code. They fixed that. We got $500 for reporting that.
To our point.
So.
Easy bounties. You look at this stuff, you get easy money just sitting there waiting for people to look at. Now, again, in Chrome, it's as simple as just clearing your cache. I believe that's what the change was. I could be wrong. If anybody from Chromium is here, shout at me or come to the mic and shout at us. It's fine. And in Firefox, about config, security, cert pinning, enforcement level to 0, visit the site again, which takes the new header on, and then re-enable, set it back to 1. Source. Okay. GitHub.com/site/ransom PKP. I think all we have up here is a proof of concept.
Not actual ransomware.
Yeah. Not actual it's a proof of concept. That's it. All right. Hat tips. So we've actually got a long list, but the biggest kudos that we do want to give, Jim Rennie came out of the shadows, to give us some counsel on this talk. His background having been at GitHub as their privacy and security counsel. He came out of the shadows to help us out because the EFF represents Let's Encrypt, and so it would have been a bit of a conflict. As much as the EFF would have wanted to, it would have been a bit of a conflict for them to represent us here. Of course, huge thanks to the Chrome, Firefox, and Let's Encrypt teams. We had a number of people that helped review our talk. So if you want all the links, that has a full list of all the links we've shown. Source, all that other fun jazz. Take that picture. If you have any questions, I don't know how many minutes we have. 7.
7?
We got questions. Go for it. Throw us anything. That's it. I mean, we're done, basically.